Coronal mass ejections, CMEs, are vast bursts of solar wind and magnetic fields rising from the solar corona and releasing a massive amount of energy and plasma into space. These solar phenomena are responsible for some of the most intense space weather events, impacting both near-Earth space environments and other planets in the solar system. The study of CMEs is fundamental to understanding the Sun's behavior, space weather, and its potential effects on technological systems, human health, and planetary atmospheres. This essay delves into the morphology, science, and observational techniques of CMEs, shedding light on their formation, dynamics, and their interactions with the Earth's magnetosphere. Morphology of coronal mass ejections. The morphology of a CME refers to its structure and characteristics during its formation, propagation, and interaction with other solar phenomena. CMEs are complex and dynamic structures that evolve over time. The main components of a CME include the following: core, plasma cloud. The core of a CME consists of a large mass of highly ionized plasma, predominantly hydrogen and helium. This cloud is ejected from the Sun at high speeds, ranging from 300 km/s to 3000 km/s, and carries the Sun's magnetic field embedded within it. The size of a CME's core can span up to 100 times the Earth's diameter. Magnetic field structure. CMEs are intricately tied to the Sun's magnetic field. As the Sun's magnetic field lines become twisted and stressed, they break and reconnect, releasing energy in the form of the CME. The magnetic field within the CME carries with it a helical or spiral structure, known as a magnetic flux rope. The flux rope is a fundamental feature of CMEs, influencing the direction and speed of the ejected plasma. Shock front. As the CME travels through space, it often creates a shock front ahead of it. The shock front is formed when the fast-moving plasma interacts with slower-moving solar wind or other objects in space. This shock can accelerate energetic particles, leading to phenomena such as solar energetic particle (SEP) events. Halo CME. A halo CME is a particular type of CME observed when the eruption is directed toward Earth. In this case, the CME appears as a bright halo surrounding the Sun in images, a result of the ejected plasma moving directly towards the observer. This geometry makes it easier to track and study CMEs. CME morphology and observations. Observations from space-based telescopes such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, reveal the dynamic evolution of CMEs, from their initial eruption to their propagation through the interplanetary medium. The morphology can change based on several factors, including the velocity, angle, and the complexity of the magnetic field structure involved. Science behind coronal mass ejections. CMEs are primarily driven by the Sun's magnetic activity, specifically the magnetic reconnection process that occurs in the solar corona. This section explores the key scientific processes and phenomena behind the formation, acceleration, and dynamics of CMEs. Magnetic reconnection and solar flares. CMEs are often associated with solar flares, which are sudden bursts of radiation originating from the Sun's surface and outer atmosphere. These flares are caused by magnetic reconnection, a process where opposing magnetic field lines break and reconnect, releasing vast amounts of energy. During magnetic reconnection, plasma is heated to millions of degrees, and part of this energy is released as a CME. CME initiation. The process that triggers a CME involves the destabilization of a magnetic configuration in the solar corona. This typically occurs in areas of high magnetic activity, such as sunspots or active regions, where the magnetic fields are especially strong and complex. When the stress on these magnetic fields exceeds a certain threshold, they snap and reconnect, launching a CME. Acceleration of plasma. Once the CME is initiated, the plasma within the magnetic field is accelerated. The process of acceleration is not entirely understood, but it is thought to involve both electric and magnetic forces. CMEs can reach speeds of up to 3000 km/s, with higher velocities typically linked to more energetic eruptions. Interaction with solar wind and the heliosphere. Once a CME is ejected into space, it interacts with the solar wind, a continuous stream of charged particles emitted by the Sun. The CME's propagation through the heliosphere can influence the structure of the solar wind, leading to disturbances known as interplanetary CMEs, ICMEs. These disturbances travel outward and can affect the Earth's magnetosphere when they reach it. Magnetic field reconnection in space. When a CME impacts the Earth's magnetosphere, it induces magnetic reconnection between the Earth's magnetic field and the CME's magnetic field. This interaction can cause geomagnetic storms and auroras, leading to significant space weather effects. Observational techniques and detection of CMEs. Observing and studying CMEs is critical for understanding their behavior, predicting space weather events, and mitigating their potential impacts on Earth. Several tools and techniques are employed to detect and characterize CMEs. Space-based telescopes. Space observatories such as the SOHO, SDO, and Parker Solar Probe have revolutionized the way CMEs are studied. These telescopes operate in various wavelengths including visible light, ultraviolet, and X-rays, allowing scientists to observe different layers of the Sun's atmosphere and capture the onset of CMEs. SOHO, launched in 1995, has a suite of instruments that have observed CMEs in detail, including its LASCO, large-angle and spectrometric coronagraph, instrument. This tool captures images of CMEs by blocking out the Sun's bright disk and revealing the structure of the corona. SDO, launched in 2010, provides high-resolution images of the Sun, including the solar corona and chromosphere. Its AIA, Atmospheric Imaging Assembly, is used to study the dynamics of solar eruptions. The Parker Solar Probe, launched in 2018, is in a unique position to observe the Sun's corona up close, providing invaluable data about the inner workings of CMEs. Radio observations. Radio telescopes are used to study the plasma waves generated by CMEs as they move through the solar wind. These waves can provide clues about the velocity, size, and magnetic structure of the CME. Radio bursts produced by CMEs can also give insights into the shock waves created by the ejected plasma. Interplanetary monitoring. Once CMEs leave the Sun, they can be tracked through their interactions with spacecraft positioned between the Earth and Sun, such as NASA's STEREO, Solar Terrestrial Relations Observatory mission. These spacecraft can detect the arrival of ICMEs at different positions in space, helping scientists study their properties and estimate their arrival time at Earth. Ground-based observations. Ground-based observations, especially through magnetometers and all-sky cameras, can track the effects of CMEs on the Earth's magnetosphere. These instruments are invaluable for studying the geomagnetic disturbances caused by the interaction between a CME and the Earth's magnetic field. Impacts of CMEs on Earth and space weather. CMEs can have significant consequences for Earth and its surrounding space environment. When a CME reaches the Earth, it can trigger a variety of space weather phenomena, including geomagnetic storms. A CME's impact on Earth's magnetosphere can result in a geomagnetic storm. During a geomagnetic storm, the Earth's magnetic field becomes disturbed, which can lead to disruptions in satellite communications, GPS systems, and power grids. These storms are often associated with intense auroras, or northern and southern lights. Spacecraft and astronaut safety. CMEs can present a significant hazard to astronauts and spacecraft. The energetic particles accelerated during a CME can pose radiation risks, potentially damaging satellite electronics and affecting human health in space. Impact on Earth's atmosphere. A particularly large CME could induce changes in the Earth's upper atmosphere, potentially increasing the drag on low Earth orbit satellites, shortening their lifetimes, and impacting their operation. Technological and infrastructure disruptions. Geomagnetic storms induced by CMEs can cause voltage surges in power lines, leading to power grid failures. Telecommunication systems and satellite-based navigation can also be disrupted, potentially affecting global communications and transportation. Conclusion. Coronal mass ejections are a fascinating and complex phenomenon that plays a crucial role in space weather and our understanding of the Sun's behavior. The morphology, science, and observational techniques surrounding CMEs are deeply intertwined with the Sun's magnetic activity and space weather impacts on Earth. Advancements in observational tools and models continue to improve our ability to predict and mitigate the effects of CMEs on Earth's technological infrastructure and human space activities. As we continue to explore space, understanding CMEs and their behavior remains central to ensuring the safety and stability of our increasingly technology-dependent society.